All right, let's just jump right into this explainer because today we're unpacking a claim from the absolute cutting edge of theoretical physics that is literally mind-bending. We are talking about the idea that our entire universe, with all its 3D depth and massive galaxies, might actually just be a two-dimensional hologram projected on the night sky. I know it sounds straight out of science fiction, but we're going to dig into the actual source material from a fascinating lecture on quantum gravity to see exactly how physicists are arriving at this wild idea.
And hey, don't panic at the complex physics. Here is our roadmap for the explainer. We'll start with the quantum gravity quest, look at escaping the gravity box, uncover the secrets of flat space, examine the memory effect, break down celestial holography, and finally, check out the ultimate physics compression. Section 1, the quantum gravity quest. Let's start right at the core of the problem that theoretical physicists have been agonizing over for decades. So the fundamental issue is that we're on a quest to merge two completely different rulebooks. On one side, we've got the physics of the incredibly small, right? Quantum mechanics. This describes particle structure and high-energy interactions. Then, on the flip side, we have the physics of the incredibly large, general relativity, dealing with curved spacetime and massive objects like stars. The problem is, when you try to merge these two descriptions mathematically to understand something like a black hole, they completely clash. The math just breaks down and spits out these nonsensical infinities. Since bridging these two worlds directly seems practically impossible, theoretical physicists asked a brilliant, kind of cheeky question to find a workaround. As one researcher literally put it, quantum gravity's hard. Can we just cheat? And that brings us to our ultimate cheat code, the holographic principle. The whole idea here is that any theory of quantum gravity might have an equivalent lower dimensional description that just doesn't include gravity at all. So instead of banging our heads against the impossibly hard math of 3D gravity, we just map it to a simpler flat surface where gravity simply doesn't exist. You solve the math on that flat surface, and boom, you get the answers for the 3D space. Section 2, escaping the gravity box. But, this is where the plot thickens, because our best cheat code comes with a pretty massive catch. So the most famous version of this cheat code is something called ADS holography, but it only works if gravity is trapped inside this theoretical box with a negative cosmological constant relying heavily on string theory geometries. The massive catch? That absolutely does not match our actual universe. Our real world is what physicists call asymptotically flat. Its cosmological constant is essentially zero. The old cheat code demands a gravity box, but we don't live in a box. Section 3, secrets of flat space. To actually adapt this cheat code for reality, physicists couldn't rely on the safety of that theoretical box. They had to look way outward, to the very edges of our flat spacetime. Now, what's incredibly cool here is how moving infinitely far away reveals this bizarre, infinite escalation of symmetries. Normally, we just think of basic symmetries, right? Moving left, right, rotating. But at the boundary of flat space, what they call null infinity, there are infinite symmetries. You get things like super translations, which means you can literally shift time differently depending on exactly which angle you're looking at in the night sky. You also get super rotations. It is this incredibly rich mathematical playground that just suddenly popped open. Section 4, the memory effect. Okay, if infinite symmetries and super translations sound like purely abstract math to you, let's ground this. Let's look at how they leave a literal physical imprint on our reality. Let's look at what physicists call the memory effect, which is the physical proof of those wild symmetries. Picture a gravitational wave from two colliding black holes passing through a detector, like the massive LIGO facility here on Earth. The wave passes through and physically moves the mirrors. But here's the crazy part. After the wave is completely gone, the detectors don't just snap back to exactly where they were. They stay permanently shifted at a new baseline distance. The fabric of space has literally been permanently stretched by the energy that passed through it. Section 5, Celestial Holography Explained. Connecting those infinite symmetries to the physical memory effect gave physicists the exact tools they needed. And this brings us to the climax of our detective story, a completely new kind of holography. Researchers made a massive conceptual leap here. They boldly conjectured that we can bypass the whole gravity box problem entirely. By using those rich symmetries at the edges of our universe, they posit we can map our reality onto what's called a 2D conformal field theory, or CFT. It's basically a special kind of physics theory where angles are perfectly preserved, but scale can change. Think of it like a highly complex, infinitely zoomable mathematical drawing. So you might be wondering, where exactly does this 2D map live? Well, it lives on the celestial sphere. You can picture the celestial sphere as a cross-section of null infinity. It's the ultimate boundary where all massless particles, like light, eventually end up. In plain terms, it's basically the 2D night sky surrounding us. And the equation we arrive at is basically magic. This means that incredibly complex, four-dimensional particle collisions happening in a real, flat universe can be calculated purely as 2D interactions projected right onto the edge of the sky. You literally take a massive 4D headache, run a specific mathematical transform, and calculate it as a simpler 2D correlation on the celestial sphere. Section 6. The ultimate physics compression. So why do theoretical physicists spend their entire lives trying to prove this deeply complex mathematical connection? What's the so what here? Ultimately, it's all about the beautiful pursuit of data compression. Physicists believe that nature is fundamentally simple at its core. They are hunting for a hidden underlying code that explains wildly different energy scales without all the heavy mathematical baggage. They want to compress the massive, contradictory frameworks of modern physics into one singular, elegant truth. This is exactly why celestial holography is such a breakthrough. It isn't just a clever math trick, it's a unifying framework. It takes the tedious, sprawling calculations of traditional particle physics, I'm talking about drawing hundreds of complex Feynman diagrams, and compresses them into elegant, solvable 2D equations. By leveraging the rules of 2D conformal field theory, researchers can essentially bootstrap their way to the answers, reconstructing the geometry of our entire 3D universe using only the 2D data painted on its edges. So, as we wrap up this explainer, I want to leave you with this incredible thought to chew on. If the absolute source code for gravity and quantum mechanics fits perfectly, and honestly more elegantly, onto a two-dimensional celestial sphere at the boundary of space, what is the true nature of this three-dimensional reality we walk around in every single day? Is it really just a projection? The physics suggests that figuring out the answer to that question might just rewrite everything we know about the cosmos. Keep looking up, and I'll catch you in the next explainer.